Here we're going to talk about action potentials and nerve impulses. And what that means is that we're going to be talking about a portion of the neuron known as the axon, bracketed here. And what we want to do is focus on how the axon is adapted to transmit electrical signals over a much greater distance than the dendrites are generally capable of doing. And what allows and what provides this ability is the presence of voltage-gated channels in the membrane of the axon. And so we're going to blow up this bracketed section here and come down here and look at this view. And what we see is that if we have excitatory postsynaptic potentials occurring on the neuron and arrival of that depolarizing current, remember it's electrotonic current that would travel passively to the axon initial segment, if we reach threshold, we will open voltage-gated channels in the membrane at that location. And what that does is it changes the membrane potential right here, generating a gradient along the axon, right? A voltage difference between where the sodium influx has occurred and downstream where it has not yet occurred. And so we get electrotonic current, which is passive but blazingly fast. Now, at the adjacent segment of the axon, instead of like in most dendrites where it would just sort of dissipate with distance, what happens here is that we reach threshold of adjacent channels, causing more sodium influx and regenerating that change in membrane potential. And again, if we come down to the graph here, we can see that original excitatory depolarization that gets us to threshold. Right? We get our sodium influx causing dramatically more depolarization. But then with distance, that's going to start to wane, right? That electrotonic current wanes due to this current leak out of the cell. And so our change in membrane potential dissipates and dissipates, but before it dissipates to nothing, it reaches the next voltage-gated channel and opens it, and we get another spike in sodium influx and depolarization. We get more electrotonic current, and we repeat this cycle over and over and over. Now, the individual voltage change at one location is known as an action potential. The positive feedback loop of an action potential generating electrotonic current that generates the next action potential, which generates more electrotonic current, and so on and so forth, generates what's called a nerve impulse. And that's that propagated transmission of a membrane potential change along the axon very quickly.